AP Review Lesson 10. In this lesson we'll take a look at some free response questions concerning acid-base equilibria. So we're just going to look at one, and this actually involves a table. So let's familiarize ourselves with this table before we go further. So we have a 1.22 gram sample of a pure monoprotic acid, HA, which was dissolved in distilled water. So we just have weak acid. And the HA solution was titrated with some strong base, sodium hydroxide, 0.250 molar strong base. And so the pH was measured throughout the titration using a pH meter, most likely, and the equivalence point was reached when 40 mils of the sodium hydroxide was added. So this actually right here, this point, is our equivalence point. We call that the equivalence point is the point at which all the base neutralizes all the acid. And so we're going to be asked some questions about it. Question 1 says, explain how the data in the table provides evidence that HA is a weak rather than a strong acid. Now, we call that a strong acid when a strong acid is completely neutralized. What you're left with essentially is salt and water, which is neutral. And because that salt consists of an anion from HA, say HCl, say if we were to do HCl, the anion of HCl is Cl-. So Cl- is neither acidic nor basic, so the water will be ruling the pH. In that case, the pH will be 7.0. But because our pH is not 7.0 but higher, this means we have a weak base left in the solution, which means we began with a weak acid. So we can say because the equivalence point pH is higher than 7, the acid must be weak. Now for the AP exam I would write out, I wouldn't shorthand it, I would go ahead and write it out, but I think for the purpose of review we can take a shortcut. Write the balanced net ionic equation for the reaction that occurs when the solution of sodium hydroxide is added to the solution of the weak acid. So what we have is the HA will react with sodium hydroxide. Now we want the net ionic equation, which means sodium will be actually a spectator ion. Because remember, when you throw sodium hydroxide in solution, since it's very soluble because of sodium, it'll dissociate. So effectively we'll have OH- in the solution, reacting with HA. And an equilibrium will result. OH- is our base, and HA is our acid. So the base accepts a proton and ends up as H2O. The acid gives up a proton and ends up as A-. And this is our balanced equation. It's actually very simple. And everything balances. The charge is balanced, the mass balances. And next says calculate the number of moles of HA that were titrated. So what we have to do, and we're assuming at the equivalence point, so we want to find out how many moles we have, and we'll go from moles of base to moles of acid, because at the equivalence point those two are equal. So remember, moles is molarity times liters. Now our molarity for the base is 0.250 and our liters is 0.040. So let's combine these to find out how many moles we have. So we have 0.250 times 0.040 liters. Again, this is just a molarity calculation. So multiplying these two together, go ahead and do this in your calculator. We should get ourselves 0.01 moles of the OH-, of the base that was added. But at the equivalence point, this is the same amount. That's what they call the equivalence point. You have an equal amount of acid, 0.01 moles of HA. So this is the answer. As long as it's a 1-to-1 mole ratio, and we have no reason to think that it's not. In fact, it's HA, so it's a 1-to-1 mole ratio, so that works. Next, they want us to calculate the molar mass of HA. That's simple enough. Molar mass is grams over moles. The grams of the acid was given to us as 1.22. Let's just plug that in. 1.22 over 0.01, and dividing by 100th is the same thing as multiplying by 100. So this should be simply 122 grams per mole. So notice we were able to use a titration to determine an unknown molar mass, which is the whole point of titrations. How about this? The equation for the dissociation reaction of HA in water is shown below. We've seen this before. Assume that the initial concentration of the HA solution before any sodium hydroxide is added is 0.200. Determine the pH of the initial HA solution. So what we're saying is we're not adding any base yet, so the pH of the solution is simply due to that acid. Now, in order to get the pH of weak acids, we have to set up the icebox. Remember, the pH of a strong acid is simply the negative log of its concentration, because a strong acid completely dissociates 100%. A weak acid does not. That's why we have to use an icebox, because we have to look at it through the eyes of equilibrium. So setting up the icebox, let's go ahead and do it here. It's simple enough. So we begin with 0.200 of our HA. Remember, we don't really care about water. It won't go into the equilibrium expression. And we assume these to be zeros. And as we get to equilibrium, we lose on the reactants, we gain on the product side. So you have X, and this is 0.200 minus X. So now our Ka will equal products over reactants. This here equals Ka, which means Ka, which is 6.3 times 10 to the negative fifth, equals X squared over 0.200 minus X. Now recall, this is when we used the shortcut, and the way we used the shortcut is we actually ignored this minus X to make the problem solve easier. And we can do this as long as our initial concentration is 3 orders of magnitude different from our Ka, and here it's 5 orders of magnitude, actually more like 4 orders of magnitude. So we're within our rights to do this. So we can actually get rid of minus X, and the equation simplifies. I'm going to move the 0.200 here. So we got ourselves 0.200 times 6.3 times 10 to the negative fifth equals X squared. So I'm actually going to get rid of the X squared by square rooting the left side. And here's what we get. Now recall we gave you the shortcut to this sort of problem. And the shortcut involved, it said this: H plus is equal to the square root of HA times Ka. And that's exactly what we have. HA is our concentration of the acid. Your Ka is that number. So you simply square root it and you get your H plus. So from then you can just negative log it and you'll get your pH. So go ahead and do the calculation there. 0.200 multiplied by 6.3 times 10 to the negative fifth. Square root that, and you should get H plus to be 0.00355. And if you negative log it, you'll get the pH. Let's negative log that number. And our pH comes out as 2.45. And that's our pH. So think through this. This is a very important skill to be able to get the pH of a weak acid, and that's essentially what this is. Okay, and we'll finish up with part F. Now let me clear the screen here so all disappear. In part F, what we have is actually we're setting up a buffer. Now we're setting up a buffer by adding some strong base to our acid. We're not going to completely neutralize the acid. We will have some acid left over. And the reason we know this is because the equivalence point, remember, is whenever we have 40 milliliters added. Because we're only adding 30 milliliters, we have a buffer. We're not at the equivalence point. And they want to know the H3O plus concentration of that. So let's go ahead and, if we recall, for this we used a BCE box, beginning, change, and equilibrium box, which was different from the ice box in that we're actually going to be neutralizing and the HA with the added base. So we'll still, and for the BCE box, we have to use moles. Use moles because we are titrating, which means we're reacting base with acid. And anytime you do a reaction, you have to do it on the basis of moles, because that's what the balanced equation shows. So let's find out first how much we begin with of the acid. In order to find that, we can do here, looks like it says the total volume is 80 milliliters. 30 mils of the sodium hydroxide was added, which means we have 50 milliliters of acid. So in order to find out how many moles of acid, we can do the molarity of the acid, which is 0.200 times the liters of acid. So we get ourselves the moles of acid will be, you can put moles of acid, will be 0.200 multiplied by 0.050. So that essentially gives you 0.01 moles of the acid. So that's what we begin with, 0.01 moles. Again, the water we don't really care about. So let me leave that space open. The water we don't really care about, and these we don't really care about. These could be zeros. So now, as we're titrating, the change will essentially be however much base we add to neutralize the acid. So because our we have 30 milliliters, and our original concentration of the base is 0.250 molar. That's what the original problem said. If you go back, let's find out how many moles of base we add. So we have 0.030 liters multiplied by 0.250, and essentially 3 times 250, that's 0.0075. You have a calculator for this section, so don't be afraid to use it. But this is how many moles of base we add, OH minus, which means that's how many moles of the acid will be neutralized. So we will put minus 0.0075 here. Anytime we lose on this side, we gain plus 0.0075 here, and plus 0.0075 here. And actually, we just care about the conjugate base. We don't really care about this amount. So at equilibrium, go ahead and calculate these two. Let's go ahead and we got 0.01 minus 0.0075. So we have 0.0025 left of the acid, and we have 0.0075 of the conjugate base. This is the conjugate base, and this is the acid. So these are what we have in the buffer solution. Here is our buffer. Now, there was a buffer equation, and I would probably suggest using the buffer equation to determine the H+. And the buffer equation actually went something like this. And you'll have the buffer equation for your viewing pleasure on the AP exam. The buffer equation said that the pH is equal to the negative log of the Ka plus the log of base over acid. And this is your conjugate base and your acid. So let's really just plug and chug. Your negative log of Ka would be the negative log of 6.3 times 10 to the negative 5, this value here, plus log of your base is 0.0075 over your acid, which is 0.0025. Go ahead and plug all this in. I'll give you a minute because we're kind of running out of room. But I would do 0.0075 first, divided by 0.0025, which gives you 3. And then take the log of 3. And then, so we got, essentially we got plus 0.477. And then evaluate this amount, 6.3 times 10 to the negative 5th. Take the negative log of that, and that gives you 4.2. 4.20 to be exact. Add the 2, and you got 4.677. So your pH is 4.677. They want the H3O plus. Well, we can readily get H3O plus from pH because H3O plus concentration, if you undo the negative log idea, is 10 to the negative pH. So really 10 to the negative 4.677 gives you, and this will end the party, 10 raised to the power of 4.677 will give you 2.1 times 10 to the negative 5th molar, and this is the final answer. So this is your H2O plus. So quite complicated. I would submit that this is probably one of the most complicated questions on the AP exam. So don't be afraid of it. Do your best. If you can only get one portion of it, that would be good. So let me just cycle through the rest of the questions in case you don't get them from Edmodo. Here are the rest of the practice problems. Try this one. Pause as needed. Number 12. 13. More love here, and even more here. How about some pH curves? A few diagrams for your visual pleasure. Short questions, long questions. Another few diagrams. And this is your re-response. And I apologize for that cutoff there. But we've gotten to know each other by this point, so we're good. Okay, and this concludes lesson 10 of the review.